Yeah, you guys should be pretty good with this. Like, if you do 2 over x, that obviously just goes towards 0. So you have 0 plus 1. And the next one, because the degrees are the same, I mean, once you get very good at this, you can sort of just use those shortcuts. Like, well, I see the same degree for both top and bottom. So if x is approaching infinity or negative infinity, what does that become? We have 5x squared minus 1 over x squared. Just 5. Good. So that limit is just going to be 5. And that's true for both positive and negative infinity. There's nothing weird with absolute value or things like that. So should get 5 for 22. For 25, you have cosine x over x cubed minus just 2, right? When you break apart the fractions. And if x is approaching infinity or negative infinity, this fraction is going to go towards 0, right? Because the top is limited with its range. But of course, x cubed has no boundary, right? So that's 0 minus 2, so you should get negative 2 for that one, for 25. And sorry, yeah. And then lastly for 28, sorry, 26. Did I put 28? I did put 26. Sorry, that looked like 28. Okay. Yeah, for 26, um, yeah, we know what to do here. Again, break apart the fractions. You should have sine x over 2x plus cos x over x squared. But here's the thing. Each is going to be 0 regardless, right? Because again, the numerators have boundaries, right? There's this limited range from -1 to 1 for both sine and cosine, but 2x and x squared both increase or decrease that bound. That's still 0. So you should get 0 for 26. At least I think so. If you disagree, please let me know. So questions, yeah. Lucas.
Like on the test, would this be like expected amount of work time to show? Like,
Okay. How should you show this? Okay, great question. Okay, formally for 22, let's say, right? Let's say the limit as x approaches, and I do have your quiz grade, just haven't put them in the system yet. Um, so I will do that when I get a chance. And I have not, unfortunately, I've not had a moment to think about the test, but I will see you guys tomorrow. So I will have an opportunity to share that by tomorrow. If I do have some of my thoughts later this afternoon, I'll put it in Schoology so you guys can see that. So you have that first, right? By the way, the one thing with limits is that you do have to put brackets or write the limit for each individual part. Some of you guys didn't do that. I took off a half point if you didn't do that because you have to think about it. If you don't have the brackets, do you see why this would be a problem if you don't have brackets? Why would there be a problem? Because of what, like, very fundamental property of math that you guys talked about. So PEMDAS, please excuse me, dear Aunt Sally. That's an operator. It's only gonna, yeah, we see, if I see this, it's only gonna apply to this and not to that, right? I mean, I know you need to do it for everything, but when I see this, and actually, the College Board's very strict about that. Like they get super, super detailed. Just so you know, the way AP grading is done, they send like thousands of teachers to Kansas City. That's where they do the grading for AP calculus, and they spend like literally like 2 weeks just grading like one part, one problem, and then you're part of a table group, and then you have a group leader that actually makes sure everyone's doing everything correctly. And you just really just grade one little part of like a one free response question, and you get so good at it, and they get so detailed. So I do want to just give you that heads up, just that habit that we want to form now, because you know you're not taking AP Calcs for at least a few more months. You got to do this because you're applying that limit to the whole thing. So just keep that in mind. Just one thing I want to say. Okay, so next up, then what you could do is you could take the limits of each of these individually. So you got this, right? Times the limit as x approaches infinity of this. Now, fortunately, this one's already all set because that's going to be 0 plus 1. So you can show that. That's fine because now you're applying the limit to each of those parts inside the parentheses. That's a-okay. And actually, I am okay. Well, no, you actually do need to do this. We should actually be a little more formal. You do need to actually show that you're dividing each by x squared. And then you have 1 times the limit as x approaches infinity of what? 5 minus 0 over 1. And then you can say 1 times 5, which is 5.
Oh, so we have to write out everything that we're like dividing by?
Yeah. So you asked the question, Lucas. Yes, this is what I want to see. Yep. I want to see this. And this is now recording, so you guys have access to this, right? So yeah, that's the formality of what I need to see. Okay, let's keep moving. For 42. I mean, you guys should know that's just 3. Um, and this one you should know it's just gonna be infinity, that one. Because what's happening here is you're gonna have 4x squared. Ultimately, you have 4x squared minus 0 plus 0 over oh, sorry, minus 2. My apologies. Because you're dividing everything by x. Uh-oh. Something's not good. Anyhow, it's gonna be infinity. So that's the behavior model for 43. Because what I'm doing is I'm multiplying top and bottom by what again? 1 over. Yeah, you always want to do the highest term in the bottom or the degree of the bottom. So that way, at least you're not dividing by 0. So x times 1 over x is 1, minus 2 over x, that just goes towards 0 when x is going towards infinity. But 4x squared minus 2, well, if you think about it, that's just a parabola, right? So your end behavior model is like a parabola. As x is approaching infinity, of course, y is going towards infinity, and vice versa if x is going towards negative infinity. Sorry, and likewise, if it's going towards negative infinity. So we're cool with that. That's page 8. That's in much detail as I could probably share with that. Here I think I do have the answer keys for this. So let's because I did assign that right. Yeah, 25, 28, 29, 30. 25, 29, 33. Hold on. Oh, 40, 50. I skipped. Okay. Yeah, I skipped that. I didn't feel like that was necessary. So if you go to the answer key for that under homework 7, maybe should be there. Just save time so I don't have to review all these problems. Homework number 7. Yeah, here we go. So those are extended functions. And by the way, the piecewise function is always a guarantee. Just make the second expression the y value to plug the hole in, right? You want to plug in that hole. So hopefully that makes sense. Actually, I would just probably just do the piecewise function as always a guarantee. But you did have that option for 25 and 29 to simplify if you wanted to. Yeah, that's an option. Not we didn't have the option for 28 because it's trigged. But hopefully that makes sense for those problems. And then for 48 and 50, I told you I love these problems. The force issue continuity. And this is the work I have to see. You have it modeled now. It's modeled for you. Gotta go give me the first condition. Does f of 2 exist? Does a limit exist? And you guys show the left and right hand limits being the same. And that's what happens. We set them equal. And then of course, does the third condition work? And it does. Actually, if you do this, you get full credit. You got a model. Just copy it. That's it. Likelihood 50. You got your model right there. So hopefully that makes sense for that one. And the algebra is not hard. I mean, I know you guys can solve 2a plus 1 equals 7. That's fine. So it's pretty straightforward. Okay, we're cool with that? Okay, good. Nice to have that answer key there so I didn't have to redo those problems. And then finally for page 10, A, B for 1 and 2, A through D 3, and then number 6. That one I probably have. The answer is all laid out as well. Maybe. Yeah. For 2, actually, maybe not. Yeah, maybe not. Okay. It's all right. I can just talk about it really fast. Should be pretty quick. So again, this is 1 and 2 on page 10. Okay, so yeah, if I do a sign chart, negative 5 halves and 1, positive, negative, positive, we would agree. Approaching 1 from the left, negative infinity. 1 from the right, positive infinity. Cool with that? This one here, x plus 3, x minus 2, x minus 6, negative 3, 2, and 6. Positive, negative, positive, negative. Approaching 6 from the left, negative infinity. 6 from the right, positive infinity. Cool? Good? Okay, awesome. And then here, ooh, that factoring's fun. X minus 5. 2x x plus 1 minus 3. Like that. Yeah, cool. So -1, 3 halves, and 5, we'd agree. Okay. Plus, minus, plus, minus. Okay, approaching -1 from the left, negative infinity. -1 from the right, positive infinity. 3 halves from the left, positive infinity now. And 3 halves from the left, negative infinity. Sorry, 3 halves from the right, negative infinity. So if that makes sense for that one, we're good with that. So the sign chart is essential. And graphically speaking, it's going to look like this, right? You're going to have an asymptote here, an asymptote here. There's a horizontal asymptote of this. Graphically, you're going to have that. And then it crosses, hold on. Yeah, it has a y-intercept of 5/3, so it does this. And then, of course, then you have, did I do that right? Yeah, and it crosses at 5. There we go. Yeah, so it kind of does something kind of funky like this. We're okay with that? I think I did that graph right. Yeah, anyhow. But you can see that's what's happening with asymptotes. But see, the limits enables you to do this graph more accurately, right? So one thing, actually, I'll tell you right now, a question I'm probably going to ask. Actually, I just thought of right now. This is what I want to do. I want to do this. I'm going to have you graph something like this, and then ask you to dodge these limits in this manner. This will help you make a good graph. And I'll say, yeah, now tell me the limits x approaches infinity, x approaches negative infinity. Give me these left and right hand limits for these vertical asymptotes. So that's most likely, and then I'll probably do likewise with a polynomial function. That's what we'll do. And of course, the stuff we have in the quizzes, like those limits, I'm gonna ask that, right? Continuity, I'm gonna ask that. Extended function, I'm gonna ask that, right? I'm gonna ask all these things, and what I'm talking about today.
Why is -3 an asymptote of vertical?
-3,
Yeah, and number 2.
number 2. It was not. No, it's a 0.
Oh, okay, so,
You have to consider everything makes both top and bottom 0.
oh no, I was looking at the graph, that's.
Yeah, this graph is x for number 3, not for number 2.
Oh, okay.
Yeah. I didn't label, so. And then lastly for 6, that's a fun one. Okay. Um, I would actually clean this up a little bit. Would you agree that I'm doing the substitution of these identities correctly? Yep. So you get 1 over cos x, which is basically secant x. And we know there's a bunch of asymptotes everywhere, right? And also secant of 0 is 0. But there's a bunch of asymptotes at all these locations. Pi and so forth. So I know it's going to be pi over 2 to pi is what quadrant? Second. And cosine or secant is positive or negative in the second quadrant. Negative, correct. Yeah, it's negative. We know the graph kind of looks like this. It's like these U shapes, as you would expect, right? So it's positive over here. So as I'm approaching pi over 2 from the left side, what are you going to say?
Okay, then.
Positive infinity. There we go. That's how to break that one down.
Wait, why can't you plug pi over 2 into 1 over cosine x?
What's cosine of pi over 2?
1 over 0?
Yeah, so there's some issue, right? But is it 1 over a small negative number or 1 over a big positive number? Sorry, 1 over a small negative or 1 over a small positive number? The thing is that as you're approaching pi over 2 from the left side, think about your unit circle, right? If you're approaching pi over 2 from the left side, your x values are slightly less than pi over 2. So you're still in Q1. You're still in Q1. You're awfully close to pi over 2. Pi over 2 roughly is 1.57, maybe like 1.56667. Sorry, no 6, 7 joke. So I know, good. So as you're getting closer and closer to 90 degrees of pi over 2, the cosine value is still a positive value. It's just super tiny. So you're doing 1 over a super tiny number. That's positive. Hence, it's going towards positive infinity. If you think numerically like that, use that kind of mindset. But I like using a sign chart and telling myself, well, this reduces a secant x. There you go. These are my boundaries in the sign chart. I expect y to be positive in this interval, negative in this interval. And I know there's an asymptote there because I know how secant x looks, right? We spent all the time doing that. So what's happening is I'm approaching pi 2 from the left side. That's what's positive infinity. So this could definitely be and again, will our test be non-calc? I'm going to be kind of very upfront with you guys. I'm strongly leaning towards making it non-calc because I have to. Yeah. But most likely the rest of the test should be calculator allowed or have some calculator portions to it. But in all likelihood, because something like this, I do need you to start thinking this way without a calculator. You have to be able to do that.
Like no calculator?
No calculator for a problem like this.
Not even.
9-4 function. Unless you have an accommodation from the ASC, which I don't think anyone in this room does. So, um, very, yeah. Explain the vertical asymptotes. Yeah, so secant x, we know secant x is undefined at several locations. Every pi over 2 or 3 pi over 2, because cosine 0 at those locations. So when you do 1 over that, you get 1 over 0. I try to reduce it just to make it easier to do my sign chart. You could have done for the original, but then you're definitely still looking at the same places. You're still looking at 0. You're still looking at pi over 2. You're still looking at all those locations, right? Um, if you wanted to. It wouldn't have changed anything. But I just think just to reduce it to kind of make it easier for you to figure out what to put on the sign chart, like all the partitions or the boundaries, I think it'd be easier to look at it in a simplified form as opposed to the way it is right now. That's just my opinion. Okay, I think we're good. All right. Oh yeah, this is definitely a test question too, something like number 7 or 8. Well, that'll be assigned for homework. And maybe if we have a chance, we talk about that later today. All right, so I think that's a very thorough review of the homework. We do need to get to the lesson. We need to wrap things up. So we are going to wrap things up. Here's what we're going to do. Let's go to squeeze theorem. It's a funky theorem. It's not used terribly much, but something you just got to be aware of. It's going to look a little weird from a theoretical standpoint. Once I do a problem, it'll make more sense. So what the squeeze theorem is saying is that imagine, say, f of x is squeezed in between g of x and h of x. Then the limit as x approaches some finite value for f of x will be the same limit for g of x and h of x. So let's say, for example, this is g right here. This is h right here. That's f right in the middle. So and this is c right here. We'll call it, I don't know why it's an a. That's so confusing. We'll say that's c. Change that a to a c. So the limit as x approaches c of g of x and the limit as x approaches c of h of x, let's say they're both the same value. They're L. Then therefore f of x will also equal the limit as x approaches c of f of x also equals c. Sorry, equals L. But it doesn't always have to be a finite value. It could also work for as x approaches infinity or negative infinity. Right now in the diagram, x is approaching a finite value, it's approaching c. So I wrote that down, but it could also be true if x approaching infinity or negative infinity. The squeeze theorem could still apply. So when would you use this? Like, what kind of functions does this? It's very rare. It's a very rare case. So I don't spend too much time on this. Um, so like let's look at this case here, example 14. Like if I ask you to evaluate the limit of this, that's kind of weird, right? Because if x is approaching 0, like if you think about it, if I do the limit properties, here's the issue. I have a product, right, of two separate expressions, x to the 4 and sine 1 over x. We want to make separate expressions. Sure, I could do that one. What's the limit of x approach 0 of x to the 4 power? That's just 0. You just straight up substitute. This one, I don't know. 1 over 0. 1 over 0 is like infinity. Like, I don't know. Like, this is going to be oscillating. We even saw this, that there's an oscillating nature to this. I really don't know. I really don't know what's happening about this. And because that does not exist, we cannot use our limit process. So we don't have that luxury. It's kind of ambiguous, right? So here's what you do. You let f of x equal the expression that we see inside the parentheses. And then we're going to do this. Okay. Why do you think I'm doing that? It's not very obvious. But if someone knows, then it is obvious. Once I tell you, it should be obvious. But I'm curious if someone knows why. Why do you think I chose g of x and h of x to be those values? Or those expressions?
Because they're make g of x less than to f of x and h of x.
Guaranteed, yes, that's you're on the right track, Charlie. So see, here's the thing. What's the lowest output sine could ever have?
-1.
No, even lower. -1. What's the highest it could ever have? 1. So here's the deal. Is it a guarantee that g of x is always less than f of x, or maybe it might equal it sometime?
Right what?
Yeah, because g of x is always going to be less than this, except for the one moment when sine holds what value? Because sine could hold value -1. Look at h of x. Guaranteed h of x is always higher than f of x, except for the one moment or the rare moment when sine 1 over x holds a value of 1. So the reason why we do this, note the range for sine x is this. That's why I do that. Also from a graphical perspective. You guys should know, how does x to the 4 look roughly? Like what would that look like, kind of? Almost like a parabola. It's kind of flat a little bit. That's x to the 4. I'm going to color code. We'll go light green. This would be, okay, that's crappy. I could do better than that. That's a negative x to the 4. And then this one, I think, looks like this. I think it does some sort of wacky stuff. So somehow the brown curve, I could be off a little bit, but somehow the brown curve is in between the red and green curves. There's a time where they will equal each other, but that's what's happening. So because of this, since h of x is less than or equal to f of x, sorry, I meant to say g of x, my apologies. Since g of x is less than or equal to f of x, which is less than or equal to h of x, and the limit as x approaches 0 of g of x equals the limit as x approaches 0 by h of x. And what's going to be the limit for each of those, by the way? 0. Then, by the squeeze theorem, gotta cite that. The limit as x approaches 0 of f of x equals 0. That's work I need to see. You don't necessarily need the graph. So let me highlight what I really want you guys to show. I really want you guys to show this. Okay, that's just like a 3-year-old. Sorry, my apologies. But I don't want to spend too much time highlighting. You don't need to state this. I just say this just for your own benefit, and I show you the graph for your own benefit. But really, you just got to tell me where you're letting F, G, and H be, and make your statements. That's a formality of it. Welcome to AP Calculus. This is a lot of formal stuff. So this is what's happening here. So you have another one you could do, which is not going to be that much different. It's a slight change. You're going to literally copy the same thing. What's the only thing you're going to change? G of x equals what? The next third. H of x equals what? X to the third. Great. And fx equals what? What do you see inside the parentheses? X to the third times sine 1 over x. It's literally the same thing. You're just going to just change what G, H, and F are. That's it. Change the degree 4 to degree 3. So like actually, I'll do it right now. Let me get rid of all my highlightings, my wonderful highlightings. Literally just change three, three, three. Done. That's example 15. Yeah. You can do for cosine also. Yes. 100%. Yep. Because it has the same kind of situation. Yeah, sure. Yeah, and I think there's some problems in the homework so it's just gonna practice writing it. It's not that hard. Don't overthink it. Um, yeah, there you go. Yeah, 9 and 10. So squeeze term. So that's it. Okay. So I think that's good. Okay. Another thing we need to talk about, the intermediate value theorem. Here we go. Okay, this one kind of trips some people up. Let's read a little blurb here, and then we'll go through it. So knowing whether a function is continuous on an interval, is a continuous function, or is continuous at a point is important to say of calculus. Fine, we know this. Knowing something about continuity allows us to find solutions to other situations or problems. Fine. One important theorem that deals with continuity is the intermediate value theorem. By the way, we abbreviate as IVT because we're lazy to say IVT, intermediate value theorem. Now, when you hear the word intermediate, just in general, this is not math class. What does it mean? Middle. Like for example, if you're playing tennis, you're at intermediate level. You're in the middle. You're not a beginner, you're not an expert or advanced, you're kind of in the middle, right? So intermediate means middle, right? Or like if you go to a theater production, they have intermission, right? It's in the middle. You go get snacks or use the bathroom, whatever, right? So this theorem is important. This theorem is important because it's a foundation for fundamental theorems on which calculus is built. Because there are other theorems we'll talk about in calculus down the road. Maybe not for me, maybe next year. And here's what it's really saying. I'll just kind of sort of just give it kind of layman's terms, and we'll get into the formality of it. So f of a is right here, right? F of b is right here. Okay, so f of b is high, f of a is low. You have a, b right here. A is left of b. Let's say I put C somewhere. Let's say this is C. And that's F of C, right? Is F of C in between F of A and F of B? That's all it's saying. That's it. That's all it's saying. That's why it's called intermediate value, because there's a value that's in between F of A and F of B. As long as C is where? Where does C have to be?
In between.
It's got to be in between. Can't be to the left of A, can't be to the right of B. Maybe if I'm like way out here off in the yonder, sure. It wants to come back down, sure, but it's not a guarantee. It's not a guarantee if I'm not in between A and B. So that's what it's saying, is that as long as C is in this interval, being guaranteed there is some output when X equals C that's in between the outputs for A and B. That's what they're saying. It seems very confusing when you read it. Like, if function f of x is continuous on a closed related B, then given any y value D and f of A and f of B, there will be at least one x value C, A and B where f of C equals D. And just accept it. Like, we're like, whoa, what? Like, you're deer in headlights, right? Just look at the darn graph. Like, clearly f of C has to be between f of A and f of B. But there's one caveat. You gotta be continuous. You gotta be continuous. Because if you're not continuous, then all bets are off. Because we'll give you a good example. What if you're not continuous? Like, you could do something kind of like this here. Actually, I'm trying to think of a good example. I'm actually struggling to think of a good one. Actually, let me do like a jump discontinuity. That might be better. There we go. Ah, feels so much better. So much better. There we go. Okay. Here's f of A. See, I could choose a value. Actually, not sure that makes sense.
I think you need an asymptote.
Yeah, maybe you're right. Yeah, I'm not sure that makes sense.
You would have a value,
Yeah.
or you just put two holes. You put a hole on the first thing, and a hole.
Actually, you're right. Yeah, I could do that too. Or actually, I could do this. Thank you, Charlie, for the assist there. I really appreciate that. Yeah, I could have that. That's a possibility. Let me get rid of those extra markings because it's now confusing. Yeah, who's to say F of C has to be in between F of A and F of B? If I'm not continuous, that could happen, right? That's a possibility. F of C could be much higher than F of A and F of B. C is still between A and B, but because I'm not continuous, then I can't apply the intermediate value theorem. It's only applicable when you have a continuous function. Then you could say that there's going to be some x value C. So let's see this in action. Oh, Emma, you have a question? Yeah. Yeah. That's what saying. There's at least one x value. Sure, you could have this, right? I understand what you're saying. We just did it this way to high low to make sure you understand better. But what if we had this? But remember, it's a closed bracket, so C could equal either A or B. So is there a value of C in between A and B where it'll equal F of A or F of B or it be in between? Sure, it could equal it also. That's totally fine. C could be the same place as A. It still applies. That's totally fine.
There also be a version where it goes outside, but
Where
like
C's
say it starts at F of A, it just goes all the way up, and it actually goes past F of B, and comes back down, and it comes back to F of B.
hold on. Let me make sure I understand you correctly. You're saying something kind of like that,
Yeah.
like this.
Yeah.
Sure. Yeah, because C would be right here. I mean, or the bottom line is that can you find something that would be in between the two, right? Because I understand what you're saying. Like FC could be here, wouldn't be in between FA and FB, right? Because FA and FB are in the same place. However, this is also a closed interval too, so it could equal F of A or F of B. There's still going to be some C location that's going to satisfy this theorem if you do something like this, because the output is still going to be in between FA and FB inclusive. It can include also. But we can really kind of do a lot of mind bending things. Let's see how this is in action. So here, just saying, show that this has at least one solution. See, if I ask you to solve this, you'd be kind of confused, right? Like, how would I solve that? You know, maybe you think to do this first, right? But is that factorable? No. Remember the whole P and Q thing? You could probably do that. You could, like find all the possible rational zeros and test them out using statistic division. But here's the thing: there's a possibility that none of those rational zeros will be true, and you have some really weird numbers going on. By the way, some of your solutions could be imaginary. That's a possibility as well. But since this has at least one solution, what they're asking for, does an x-intercept exist? Well, does x-intercept exist for this? What do you guys think? It has to. Why? There's a few reasons why. What's one reason? Well, before that, but how do I know that I can find a real number that makes this true? Tell me about the end behavior. One's negative, one's positive, right? So graphically, the y-intercept is -2. It's got to do something like this. Also, what's the degree here? So you have three complex zeros, or three just any zeros, whether it's real or imaginary. Two of them could be imaginary, but you can't have three imaginaries, right? Because remember, for every imaginary, there has to be it's a conjugate. You have to have an even number of imaginary solutions. You can't have an odd number of imaginary solutions for a polynomial. That's impossible, right? Because your degree is odd, there's only really two scenarios: three real and no imaginary, or one real and two imaginary. So guarantee you have a real zero. So we know this. But how do I verify this using the intermediate vacuum? So let g of x equal the non-zero side equation. So g of x will equal x cubed minus x minus 2. Okay, so we have that. Establish g of x is continuous. Well, yeah. G of x is continuous. Why? What kind of function is it? It's what kind of function? Sure, or polynomial. All polynomial functions are continuous. So you know that. Then state g is continuous Okay, the one last thing we need to do, and this is the most important thing we have to do. We need to pick x values. One that gives a negative y value, one that gives a positive y value. Why? Why do I want a negative y value and a positive y value? Because is 0 in between a negative and positive number? Yes. Since I want g of x to be 0, so this is very important. This is the most important part. Very important. Must choose an x value that makes y negative and another x value that makes y positive. That's because y equals 0 will be in between those two y values. That's why. Hence, IVT would make sense then. We need to have that. So give me an x value that makes that negative. Sure, great. So 0, -2. Give me the next one that makes it positive. 2, sure. Yeah, I wouldn't do 1. Still negative, but 2, yeah, because you get 8, you get 4, right? You have 2, 4, and 0, -2. And the graph's gonna look like this, right? Well, from the looks of it, are we touching 0 at least once? Yeah. So then say G is continuous on 0, 2. So G is um wait. Yeah, hold on. G is continuous, so I'm not sure why the extra statement's there. That seems kind of weird to me. Hold on, let me think about this one. Then say it's G is continuous on 0, 2, duh. So G is
Maybe it's G of X is continuous on, and then, yeah, maybe it's the Y value.
no, but you don't say that. That's weird. So actually, I think we need to say this. So G of X. Yeah, not sure why that's there. I'm gonna cross it off. That just seems weird to me. But since G is continuous on is continuous on from 0, 2, so um actually I think here's what you gotta say. This still seems a little weird to me. Actually, yeah, let me cross it off. It just seems just strange. So then we know this is true. Therefore, by IVT, there is at least one X value in the interval from 0 to 2 for G of X equals 0. So when you state this, you have to state the IVT, you have to give me the interval, and you have to say it equals 0. So I really need 3 things. I definitely need to see this. I definitely need to see that, and I definitely need to know that. I mean, the graph shows it. Yeah, it's just the wording that just seems off. It's not how I'd write it. It just seems, so we'll do one more example just so you guys get the hang of it, because that just seems weird to me. Um, yeah, Sophie, yeah,
Well,
Sophia.
use the IVT to just prove that there are zeros or are there other?
No, I'll tell you to use IVT for that. So
Is it like for this purpose or?
correct, only for this purpose, right? Yeah. So there's actually a homework problem. I'll show you really quickly one of the homework problems that I'll have you guys do. I think it's going to be a while ago. Yeah, here we go. Yeah, so like for example, number 1. This is on page 8 of the homework. Actually, I'll show you the solution key, just in interest of time. Nope. Let's see. I know we assigned it. There we go. So the question is, show that E of X equals X at least one solution. So this means that you move X to the other side. You're trying to put this as an X intercept. This is kind of weird. That's a really strange equation. So in order to do that, you got to pick 2 X values. One makes it positive, one makes it negative. Well, G of 0 is 1. G of 1 is that number. Great. That one you need a calculator, obviously. Well, no, I think you guys could still. I'll choose something easy for you guys to do, but not a calculator. So anyway, so what happens here? Okay, I think this is what you had to show. Okay, this was probably why I got confused. Clearly zero is between those two numbers, right? So this means that g of 1 is less than 0 is less than g of 0. So there's definitely going to be an x value between 0 and 1 where that's going to be true. And because g is continuous, because each of these are continuous, right? Each of these are continuous functions, so if you're just subtracting it, then of course that's going to be continuous on from 0 to 1. So by the IVT, there exists at least one x value where that's going to be true. But what you need is somewhere along the way, you just got to show that this is true and this is true. You got to show that, and then you make your statement. The statement again, IVT, at least one x value and your interval, and that the function equals 0. So that's your model right there. That's what's happening. Okay, so that's that. Okay, one last thing we need to talk about. Then we're really all done. Advanced limits. I know this is going to be a little crazy. So I don't have any notes on this, but the notes are pretty much done. So we are done with the notes. Hooray. That's good. Let's look at the homework packet. And I'm going to do a few of these problems with you guys and then have you guys do some for homework. And you do have some work on intermediate value theorem as well. So if you go to your homework packet, and let's actually explore the bottom half of page 12. Okay, these are going to be a little bit crazy. But you just got to be very slow about this. Not going to go fast. We'll go very slow here. Yeah, bottom page 12, yes. Yep. Okay. Yeah, let's talk about it. Okay, cool. So here we have a composite function. You're asked to find the limit as an f of x. You're not given an equation f of x or g of x, right? You're given graphs. So the first thing you do for composites, as you guys always know, always deal with the inside function first, right? So what you need to do is actually figure out first, find the limit as x approaches 1 of g of x. So if you look at g of x here, as I approach 1 from both left and right side, what do you get? 0. Great. So now we rewrite this. You find the limit as x approaches 0 of f of x. Notice how this changed. That represents the limit as x approaches 1 of g of x. So when you do these composites, what you're doing is you're applying this to the inner function using the graph. Whatever output that is, that output now becomes what you're approaching for x for the outside function. So what was g of x approaching when x was approaching 1 here? 0. So now, when you take the next step, you rewrite this limit as, oh, well, what's the limit x approaches 0 of f of x? And this is determined by that inner function. That's a pretty easy one. They get a little wild. Now let's take a look at part B. The problem with this one is that you're doing f of x times g of x, right? I have a problem here because the limit of f(x) doesn't exist at x equals 2. So we explore the left hand and right hand limits of the product. See, if I try doing this, I have a problem. Why do I have a problem with that one? Yeah, because the limit doesn't exist as x approaches 2. Um, but if I do consider um, the product of f times g as x approaches 2 from the left side and x approaches 2 from the right side, maybe I could figure this out. Maybe I could. Um, so in this case, if I approach 2 from the left side, what's f getting closer and closer towards?
0.
0. And if I approach 2 from the left side here, it's approaching 1. So in that case, sure, I get 0 times 1, which is, of course, 0. If I approach from the right side, what happens?
1.
Yeah, if I do f times g here, I'm approaching 1 times 1, which is 1. So because the LHL does not equal the RHL, the limit does not exist. Now, of course, you could just say that right from the beginning. Well, it didn't exist for f of x, but there are times where it could, depending if something else is weird is happening with g of x. There's times where it could actually. But that's what we would do. We want to break it down by its left and right hand products. Sorry, left and right hand limits of the and do the products of that.
So you have to write out 11 left hand limits of both.
Correct. Right. Now, this is the fun one. C. C is the one I really care the most about. Okay. I'll get someone Chick-fil-A tomorrow if someone can get this right. Well, no, not tomorrow. I'm too busy tomorrow, but next week. And it's not D&E, by the way. You gotta give me a good explanation as to why. And there's an answer. It's not D&E. Chick-fil-A, Charlie, you want it? Large waffle fries and deluxe sandwich with cheese, Chick-fil-A sauce. This one definitely asked on a test. I like this one a lot. It's my favorite one. I'm just gonna tell you guys. It's 0. Why? Okay. So here's just why. Let's look at the limit as x approaches 0 of fx. What's that going to be? But it's not really 2. It's 2 minus. Why is it 2 minus? As I get closer to 0, of course I'm approaching 2. But I'm approaching 2 from below. Like it's 1.999999999999999, whatever, right? Okay, now use that for the outside function. So now you're going to do this. The limit as x approaches 2 from the left side of fx, sorry, no Chick-fil-A, guys, that time, equals 0. Because if you think about it, according to this graph, it's not coming from 2 from like up above and down below. It's coming from both sides down below. So I'm approaching 2 from down below. So what happens is that, okay, so now I have to approach 2 from the left side. approach 2 from the left side, we'll just look at it at 0. So what happens is that it turns into a one-side limit when you do the outside function. So we'll explore this tomorrow. There are more problems to do, and that's it. Okay. Correct. Yes. If my graph looked like this, the answer would have been 1.
Okay.
Correct. Yes. Kind of, in some ways. We give you very simple situations. But as a composite function, yes, great. That's a great observation, Marie. Yes, No. I mean, if I just told you straight up, find me the lowest x approach to f of x, just say 2. That's fine. It's all good. Where you have to be more finer the details is when you have the composite function. And that's what I'm trying to. So it's attention to detail, guys. That's a takeaway here.
Going.
Well, that does not exist, so forget about it. Yeah, if I had this here, Laura asked a great question too. What if I had this here? Then it's gonna be D&E. Correct. Right. Because the y values are getting closer to from down below. So what is y truly? Like 1.99999999999. And if I find the limit of fx again using that, that's getting closer to 0. I know it really happens. Forcing, I think, more critical. Are we getting more critical? 100%, right? Not just level 2, it's something else. Getting deeper.
So
Great.
That's the question. That's not the question.
Yeah, there's plenty of good ones here. We'll talk more about some Thursday. So.